Hello, everybody. Our lecture today, as we continue through Introduction to Soil Science, is calcium, magnesium, and sulfur, otherwise known as the secondary nutrients. And then we'll also talk a little bit about the micronutrients as well. So I've got this nice little fun graphic here, but the material that actually comes with it is actually pretty good in kind of telling you about sulfur, calcium, and magnesium. But let's kind of get into it. So we're going to focus on the secondary nutrients. So we've got calcium, magnesium, and sulfur. All three of them are essential plant nutrients, but they aren't as essential to the plant as nitrogen, potassium, and phosphorus. And so that's what makes them secondary. But they're not micronutrients because the micronutrients are required even less than the secondary nutrients. So we got a little hierarchy. And at the end of the slideshow, I've got a graphic that spells that all out. Generally in the western soils, there's plenty of calcium and magnesium, but you're going to find sulfur to be limiting. You're not going to find a lot of sulfur out in these soils, but plenty of calcium, plenty of magnesium. Of the 7 to 10 micronutrients, depending on which papers you look at, we're only really going to focus on iron and zinc, talk about boron and copper a little bit, but mostly focus on iron and zinc because out here in the western soils, those are the most important ones. So we'll start with calcium. So it is the most plentiful soil nutrient. You can find it in feldspar, dolomite, limestone, gypsum, and a bunch of different soil minerals. You'll find calcium. So that's why it ends up being the most plentiful soil nutrient. When we talked about other minerals in the past, we haven't come up with this long list of different ways you can get a nutrient. But calcium, you can get it from all these different things. Deficiencies in calcium are rare, usually only in very sandy or acidic soils, but it can happen. Calcium's mobility is relatively low because it's tightly held in order to exchange. Sometimes the exchange gets overloaded, and because they're so held tightly together, that even sometimes the other thing to think about is that even if it leaches, it's not really considered a pollutant because it's non-toxic to animals and it's actually needed by animals in large amounts. So it's something that actually having plenty of calcium in our soil and having it in all these other soil minerals is not a bad thing, because even if we end up with extra calcium in the system, it usually works out to be okay. So just kind of an idea, just looking at them, here's just dolomite, limestone, and feldspar, what they look like, and these are the type of minerals that we can get calcium into the soil. So the primary function of calcium is plant growth. It provides structural support to the cell walls to give them some rigidity. That should kind of make sense to people if you have parents similar to mine or grandparents similar to mine who say, you got to drink milk so you can get your calcium and make your bones strong. And I think that's what they were going for, because it provides that structural support to the cell walls for plant growth. So it's important in getting real rigidity. Calcium is also a secondary messenger when plants are physically or biochemically stressed. So how do we lose calcium? So you can lose it when it's dissolved and removed in drainage water. Plants can use it up. Soil organisms can use it up. It can be leached through rainwater, and then also used up by the clay particles. When you have a calcium deficiency, symptoms in the plant would be death at the growing point, abnormally dark green foliage, weakened stems, because remember, it provides that structure support to the cell wall, shedding flour, or any combination of those things would show a calcium deficiency. So, what would soils look like if they were high in calcium versus low in calcium? This is kind of a look. You can see the soil on the right has a heavy iron content with that orange rusty color, whereas this soil on the left has a lot of calcium in it. You can kind of see those traces of white in there. Most young soils contain lots of calcium because we said there's all those different ways that you can get calcium in the soil. Older soils usually don't have calcium, as much calcium in them, because you got all those different sources when a soil's young and healthy and doing well. But if the soil's old and highly weathered and doesn't have a lot in it in terms of organic matter, in terms of plant life, in terms of soil organisms, then you're not going to have as many sources of calcium, so you're going to have much less. The plants need calcium in large amounts because the cell membranes, like we said before, that structural support, the cell membranes don't function without adequate calcium. You don't have many calcium fertilizers because it's something that you're not going to usually lack in the soil. You do have it in some soil amendments, so if you're going to use gypsum, that's you get calcium and sulfur. If you are going to lime an area, put some limestone in an area, that's also a good source of calcium, and it helps to raise pH if you're back east in terms of their soils over there. With magnesium, so the second of our secondary nutrients, there's less magnesium in soils than calcium, but magnesium is more soluble. Remember, if we put it into a solution, that we start saying, well, if we get the soil wet, are we able to actually get the minerals to exchange out of them? And so it's much more soluble than calcium. So usually there's plenty of magnesium available, especially in these western soils. Most of your magnesium comes from dolomitic limestone. Magnesium is strongly absorbed to clay particles, so it doesn't really, you don't really have to have problems or worry about problems with it leaching through the soil. Magnesium is the central atom amid 4 nitrogen atoms in the chlorophyll molecule, so it's involved in photosynthesis for the plant. It's an activator for many enzymes required in the plant growth processes and stabilizes the nucleic acids. So it's actually got a very important role in plant development with this, with it being involved in chlorophyll and photosynthesis, and then activating enzymes. If you have a plant that's showing magnesium deficiencies, it could cause chlorosis in the leaves, and then grass tetany in livestock. And the grass tetany would be the idea that magnesium is one of the essential nutrients that we need, that animals need, and so in livestock, if you're getting this, if you have a magnesium deficiency, you can have the grass just actually won't be any good to the cows, almost useless to the cows, and actually causing them problems because they won't be getting the magnesium that they need out of it. So we said you got magnesium in dolomitic limestone, so you can get that in terms of fertilizers. Not really used here in the West, but that's one way you could do it. And on the right here, this picture, that's what some versions of magnesium deficiencies in plants would look like, with that yellowing of the surface area. The one that's much more common, but it's more expensive, and you really just use for ornamental plants, is Epsom salts, which are those, if you have older people in your life, they might soak in Epsom salts, or do like stick their feet in Epsom salts. That's, at least that's where I've heard of it before. Maybe everybody's not quite the same. Epsom salts aren't actually a salt, but it's magnesium and sulfate combined together. And then the other place we're going to get magnesium is gypsum. Gypsum is going to be mostly calcium sulfate, so mostly calcium and sulfur mixed together, but there's some magnesium sulfates that are mixed in. But we've mentioned it before, gypsum is really used extensively for salty soil reclamation when we're talking about our salt-affected soils. So that's really the only place you're going to see gypsum being used. So when looking at this graphic right here, the whole story is the idea that you want to get the right balance. So you really need to understand your soil pH, because when you have acidic soils, you're going to have high magnesium, you're going to have lower calcium, they're going to be tighter and stickier soils. If you're got a more basic soil, like we do out here, you're going to have high calcium, low magnesium, where you're going to have open soils, much more poor structure, and they can collapse. If you're in that good zone that we talked about, that 6.5 to 7.5, that's where you want to be, because you can maintain a good balance where you got that 4 to 6 parts calcium and 1 part magnesium, or a 1 to 4, 1 to 6 ratio, somewhere in there. So our last of our secondary nutrients is sulfur. So it's part of many amino acids that make proteins. Like we said before, it's limiting out here in the western soils, so you can definitely end up with sulfur deficiencies in the crops out here, because it's just not as naturally occurring as magnesium and calcium are. The majority of sulfur comes from organic matter enriched soils. So if you have a soil that's lacking in organic matter, you're already going to know that sulfur deficiency is probably something that you should expect. You can get it slowly released from pyrite, gypsum, and sodium sulfate. You got many major fertilizers and soil amendments have sulfate as the anion component. So remember, we had cations and anions. Both calcium and magnesium are cations. They have the positive ions, whereas sulfur can be either positive or negative. So sometimes I think it's divalent is the term for that, where it could be either or. Some fertilizers that you'd see with sulfur in it: ammonium sulfate, potassium sulfate, popcorn sulfur, gypsum. And then there was a problem back in the 80s where it was part of acid rain, but that problem has been fixed in the U.S. because there was quite a bit of concern about that in the 80s, and they were able to clean that up. In terms of crops, I mean, sulfur is needed in fairly large quantities because it's an essential building block in chlorophyll, similar to magnesium, and also in protein synthesis. Sulfur is required by the rhizobia bacteria in legumes, so for them to be able to do their nitrogen fixation, to be able to turn that atmospheric nitrogen into the usable ammonia within the soil. But in general, crops remove about as much sulfur as they do phosphorus. So I think in the examples that I've been giving you in lab, we've been seeing problems with phosphorus in our soil, which means that one of the things we would also think about is if we didn't do a test for sulfur, we might want to, because that might also be problematic, because crops will remove sulfur just as much as they will remove phosphorus. Grasses remove sulfur much more efficiently than legumes, because legumes need sulfur for that nitrogen fixation. And then clover will disappear from pasture mixtures when sulfur is low. Clover does not do well without sulfur. Sulfur deficiencies usually show up on young leaves first, and so the leaves will appear a palish green to yellow, similar to the magnesium deficiency, but the magnesium deficiency you usually see like a lot of yellow, whereas this could just be pale green to yellow. But the other thing you'll see is that the plant will get spindly and small with retarded growth and delayed fruiting. So you'll see stunted growth, and you'll see fruiting that's not coming at the proper time of the year. You can rapidly correct a deficiency, but you have to use one of those available sulfate fertilizer sources. There are some soil bacteria that can change sulfur to sulfate, so that would also help. But the thing is, once it's in that sulfate form, it's really easily leached from soils. And so, especially in sandy soil. So the big thing is, if you have a sandier soil, you're really going to get like a inefficient use of your sulfur. And you're going to have to put a lot of sulfur on, because you're going to lose the majority of it through the soil, because sulfur's not tightly held in exchange. So we mentioned before that sulfur, you find sulfur in organic matter. So where would you have problems with sulfur? You'd have problems with sulfur in sandy, low organic matter and well-leached soils. That's kind of the trifecta for making sure you have a sulfur deficiency in your soil. So this slide right here, little out of focus. I apologize for that, but sometimes you gotta take what you can get. But it's showing sulfur in kind of the sulfur cycle and how sulfur gets into the ground and up to the plant. So you can see on the left there, we've got our sulfate fertilizer. You can get sulfur into the soil that way, and then it gets changed into that sulfate form, where it's then usable by the plant. Or you could get it through acid rain, which we talked about before, which was a problem in the 80s, but we don't really have that as much now. Or the other place you get it is organic sulfur. So you can see that we got the animals there, so we can get some sulfur in our animal residues and our poop, basically, because we talked about the idea that it comes through organic matter. Well, how do we get organic matter? Well, we get it from dead leaves and roots and branches and poop and animal residues. And so that's what we just talked about, but in picture form, if that works better for you. So those were our 3 secondary nutrients. Now we're going to focus on the micronutrients, the ones that they're still important and needed for the plant, but they're not as essential as nitrogen, phosphorus, and potassium. Those are our macronutrients, and they're not as important. Our secondary nutrients are calcium, magnesium, and sulfur, but they still have importance to our plants. So the big thing with micronutrients and why they're the micronutrients is they're needed in very small amounts. They're really needed in like ounces, up to 50 pounds an acre. Mostly they're just needed as enzyme activators. When we're looking for deficiencies, it's usually in plant material, because the interactions in soils can make large amounts of the micronutrients unavailable. So when we're saying plant material, you got to look at kind of the whole thing. Their availability is affected by more by soil pH than the macronutrients. So the graphic right here on the right, you can see the availability of elements. So as soil pH goes up, calcium and magnesium, they're fine with that. Nitrogen, sulfur, and potassium, as soil pH goes up, they're also pretty much okay with that. But then you look at the majority of our micronutrients, so iron, manganese, copper, zinc, aluminum, and you see those just drop off as the soil increases. So they're really affected by the pH of the soil. So it's really important to get the right pH. Now, what's interesting is that if you look at this, you say, oh, well, wait a minute. But 6.5 to 7.5, that's where our plants do the best. Yeah, they do, because what are the most essential elements? Nitrogen, nitrogen, phosphorus, and potassium. Well, nitrogen and phosphorus, or nitrogen and potassium, do really well there. Phosphorus takes a dip just like the micronutrients do, but it's still in that right at 6.5, and even right pretty much towards 7 before it really starts to dip off. And then your secondary nutrients are all also readily available at that 6.5 to 7: calcium, magnesium, and sulfur. It's just these micronutrients, which really goes to show you as to why they're micronutrients, because we can still have really successful plant growth even with these elements being just available in small amounts. Because remember, they only need small amounts, so it works out well. Micronutrients, though, are required throughout the growth cycle. There's no point of growth for the plant where micronutrients aren't needed. So you can see at the bottom there, so during germination and establishment, iron, zinc, and manganese are going to be your important micronutrients. During your vegetative growth, iron, zinc, manganese, copper, and boron. Your flowering and reproduction, iron and boron. Your maturity and senescence, copper, molybdenum, and boron. Chelates, or chelates, I don't know which one is proper. You can go on Google and hit the little button when you type in chelates and see what it says. But they are combinations of metal minerals with organic compounds that make up the mineral portion that's available for plant uptake in terms of these micronutrients. So most micronutrient metals must be chelated to be used quickly by the plant. The nutrient portion is called the metal. The organic portion is called a ligand. In nature, the organic portion comes from root exudates, soil organic matter, soil bacteria, or fungi, whereas commercial fertilizers of micronutrient metals most often are already in that chelated form. And so if you want to know what that means, this is what it means, and this is why it's important. So an inorganic nutrient, these micronutrients can't really penetrate a waxy leaf. They just can't get through that surface. But if they combine and become this chelate nutrient, then that is able to penetrate through the leaf. And then once it's in the leaf, then the chelated, it releases the nutrient, and the plant can take it in that way. So it kind of helps to get the nutrients into the plant. So let's focus on a couple micronutrients. So iron is by far the most important micronutrient. It's needed for chloroplast development. Could be about 30 pounds per acre in most soils, but it's very insoluble from iron oxides and sulfides. So there's not a lot of iron readily available in the soil, which we've said micronutrients aren't needed in high amounts, but they are needed. The availability is highest in acidic soils, so out in western soils, not really as available. Corn, sorghum, soybeans, and beans all really use iron, and they're all big iron fans. Most use fertilizers either applied foliarly, so to the leaves, or applied through the soil in terms of the chelates. Usually iron is put in at pounds per acre, like just a few pounds per acre, not like thousands of pounds per acre. Iron deficiencies are usually going to be more common in sandier soils because it's another thing that can leach through the soils. Iron, the best way to describe iron is that it's that Goldilocks theory, right? Too much is not good, too little is not good, and just the right amount is exactly how much iron you need. With zinc, it's our second most important nutrient out west. It's needed for good enzyme function, 2 to 5 pounds per acre in most soils. Like iron, it's mostly available in the acidic soils, so you can get zinc deficiencies out here in the basic or alkaline western soils. Corn, onions, sorghum, and many fruits love to have zinc in them, and the most used fertilizer is either applied to the leaves foliarly, or it's the chelates, or there's also zinc sulfate. And you can see the rate that you would normally apply it at in general. So things that would reduce the mobility of zinc getting into the system. So having a high amount of limestone, having a high pH, having high clay soils, having low organic matter, having low soil moisture, and having a high amount of iron and aluminum oxides. All of those things prevent zinc from working into the system and getting up to the plant. Boron, that's another one of our micronutrients. It's needed for good flower and seed production, needed for nitrogen fixation in legumes, and it's actually really important for the grape production in Kern County. It's only ounces per acre used per crop, so very little of it. Boric acid in soils comes from degrading rocks and organic matter. The main fertilizer is actually borax, which some people use in their laundry to be able to clean it up a little bit. And it comes from it's mined. You'll find if you go a little bit east from here, you can find active boron mines. It is one of those nutrients that can be toxic at certain levels to plants and then also to people. So it's got to be, you got to really pay attention, because the range between deficiency in a plant and toxicity to a plant is actually a really narrow range. So it's something to really pay attention to, because as I put here on the screen, if you have it 0.3% or less, not a big deal. But as soon as you get to 1% or more, it's toxic. So on the right there, that's what some mined boron would look like. And on the left here, boron is important to plants. It's necessary. This here is a corn plant, and so it talks about boron deficiencies. They're more pronounced during drought, if root activity is restricted. Boron can improve your seed set under stressful conditions. It's essential for the elongation of pollen tubes. It enables plants to form sugar borate complexes, which will help the sugar move through the system. It's required in even though it's required in small amounts, it helps with the cell walls and providing structural support. And then, like we mentioned before, the line between deficiency and toxicity is really narrow. So you really have to make sure to really check your plants. If you have that boron deficiency, you need to address it right away before it becomes a toxicity. Another couple, and our last couple of micronutrients we'll talk about are manganese and copper. Manganese is similar to zinc in its reaction in the soil. It can be toxic in some acidic soils, and you can correct it using magnesium sulfate. Copper is insoluble in acidic or basic soils, so you actually need to have like perfect soils to get copper to be soluble, because it's really tightly absorbed to soil particles. It's also strongly bonded to the organic matter in soils. Just like the other micronutrients, it's only needed in ounces per acre. And usually copper is added in as part of fungicides for grapes and citrus. So on the left here, talks about how copper is essential for the production of key enzymes. It helps encourage protein formation, helps move carbohydrates in the plant, and it can lead to increased lignification, which helps the plant be resistant to disease. And then also a little bit about molybdenum, which is another one of our micronutrients. So in legumes, molybdenum is the part of the process which the rhizoctonia bacteria fix nitrogen from the air. So another one of the micronutrients that's helping with nitrogen fixation. And then molybdenum helps convert nitrate nitrogen to organic nitrogen or amino acids in the plant. So I attached this this graphic here because I thought it was important in terms of what do these different what do leaves on a plant look like, and how can we tell what deficiencies we're looking at. So you can see we got boron, sulfur, manganese, zinc, magnesium, potassium, molybdenum, copper, iron, and calcium. So kind of pay attention to that, to all these different deficiencies. I'd pause it here and really take some notes, like looking at iron. So you've got the major veins are still going to be green, but there's no spots and the leaves are going to be pale. Whereas copper, you're going to have pale pink between the veins, and then you're going to have wilt and drop. If it's zinc, you're going to have the leaves being pale, narrow, and short. The veins are going to be dark green, and you're going to have dark spots on the leaves and edges. So you can look at the leaves and see all these different deficiencies. So I think it's a pretty important little chart to kind of get very familiar with. You know, if you take nothing out of this lecture except for this, I'd be happy. So as usual, I've attached some lecture quiz questions. So as with all the other lectures, you know, pause here, try and answer the questions, and then let me know if you have any questions or anything that you need help with. And with that, I will say that's it in terms of our understanding of our nutrients. Our macronutrients, our nitrogen, phosphorus, and potassium, our primary macronutrients, our secondary macronutrients, our calcium, magnesium, and sulfur, and then our micronutrients, our iron, manganese, zinc, copper, boron, molybdenum, and chlorine. We didn't talk much about chlorine, but we kind of focused on the other ones. So if you guys have any questions, please let me know. Hopefully you enjoyed it, and we got a couple more lectures.